In this video, let's talk about some Linux tools, especially Bash. I'm going to be talking quite a bit about sort of text processing tools because I feel like mastery of these things really makes you immensely more productive as a researcher who does any sort of experimental work. So let's just kind of run down an overview here. I've got sort of an overview here on the side. Let's kind of run down the list and just touch briefly on a bunch of these tools and then try to kind of go through some worked examples to see how you might actually use these tools in a realistic, experimental scenario. So let's start off with the really basics like cat, head, tail, less, and some text editors. Actually, I'll put the text editors on a separate line here. And I'm going to try to sort of annotate this file as I go with times in this video so that by the time I'm done, you guys will have a reference where you can jump back and forth to, the things that you're interested in learning about. Okay, so let's start out with the very basic stuff. I've run a command and produced this file temp.txt. If I want to view the contents of this file temp.txt, I have a few different options. I can cat it. Cat, of course, stands for concatenate. And scrolling up, you can see that was quite a large file. Maybe I don't really want to print the whole thing to the screen. I mean, I just did, but how useful was it to have that giant dump on the screen? Maybe I just want to view kind of the first 10 lines or last 10 lines or first 2 lines or something like that. So let's try piping the output of this cat command, which is the whole file, to the head command. What does that do? So it prints out the first 10 lines. And I just realized I want to talk about another command, so I'm going to probably make some notes here as I go about things I want to talk about. Okay, so head takes as an argument a number of lines. So you go -1, -2, -30, and so on. You can print out however many lines in the top of the document you'd like, and then tail is similar. It prints out the bottom of the file. So the bottom line, the bottom, 45 lines, and so on. So that's what head and tail do. By the way, you don't need to cat a file to head and tail. You can actually just go head temp. It's about the same as catting temp to head. It's roughly the same. And then there's also less. If you want to view a file in kind of an interactive console, then less works. So you can press enter to go down line by line. Press spacebar to go a whole page at a time, and it actually accepts page up and page down as well. So you can just kind of, it's almost like a text editor, but you can't make changes, like a read-only text editor. And Q is to exit. I think you can also press Control-C. No, you can't. Q. Okay, so that's kind of the basic, viewing the contents of files. How about some basic text editors? So we could edit this file with Nano. Nano is a super basic text editor. I can, can do the things I would expect, roughly home and end, take you to the start and beginning of lines, page up and page down, go up and down, right and left, navigate as you would expect. Cut and paste are sort of funny. Cut is Control-K, and then when you paste, you sort of uncut with Control-U. So you see there, cut text, uncut text. Nano is kind of nice because you actually have, roughly speaking, instructions on the bottom here. These are like the hotkeys, right? So Control-C tells you where you are in the file, line and column. Control-W is to search for something. And, Control-X is help. Exit. And when you exit, it asks you do you want to save or not. I'll just say yes in this case. And then it asks you what file name to write, so you can change the file name, save as. Okay, so that's Nano. Pico is just basically the same as Nano. I actually don't know what the difference is between Pico and Nano. Micro is sort of more interesting. This is like a modern replacement for Nano or Pico. This is pretty easy to find online and install. My installation scripts that I've talked about in other videos do install this. So Micro is just it's a modern version of this. You have full mouse support. You actually can scroll with the scroll wheel. And you can use the mouse to cut and paste and do all the things that you would expect a normal editor to do. Control F is find. Control N and P is to go next and previous once you've found. And then you can, I think at any time you can press Alt G to see kind of what the common key bindings are. Control X is cut, Control V is paste, Control C is copy, sort of standard stuff. Control S save, Control Q quit. So I'll save, I'll quit and save. So that's a quick, micro intro. How about the echo command? So this is a bash built in. It just echoes. Echo hello, prints hello. If I put hello in quotes, what's going to print? Is it going to print hello in quotes or just hello? So it prints just hello, no quotes. Why? Because the quotes are resolved at the level of the bash interpreter when it's processing all of the arguments before passing them to the command echo. Well, actually, echo isn't a command, it's a bash intrinsic, but that doesn't matter. The point is the quotes are actually processed when the bash interpreter is actually just processing arguments before passing them to an intrinsic or a command. So if I put single quotes here, you can use as well in bash, so I'm kind of getting into this quotes section. So here in the quotes section, we're going to start talking about it at, roughly, I think it was like 5 minutes and 50 seconds. Okay, so single quotes do the same thing. It appears here. Back quotes, what the heck did back quotes do? Well, back quotes end up saying command hello not found. Well, that's kind of funny. So it's executed hello. That's what back quotes do. They actually execute as a command whatever's inside the back quotes. By the back quotes, how do you generate one? It's the key to the left of the number 1 on the keyboard. It's like shift back quote is tilde. So this command, this key is the shift back quote, shift back quote. Okay, so whatever's in here gets executed as a command. And of course, there's no hello command, but there is, say, we can execute cat.txt, temp.txt. What's that going to do? This is going to, inside the back quotes, is going to execute this. It's going to cat temp.txt, so the entire temp.txt command. All of that will then be produced right here as a substitution for this whole back quote expression, and then echo is going to try to echo all of those contents. And echo, unless I specify an extra argument here, -e, which I'm not specifying, any new lines that appear in the output of this cat temp.txt will not be printed by echo. So it's going to print everything as a single line. So I'm echoing the result of the command cat temp.txt, and echo is a single line output unless I include -e. But in this case, the cat sort of recognizes that it's being used in the back quotes and it doesn't print new lines. So I normally think of whatever I'm running in back quotes as something that should produce a single line worth of output. So that's kind of a quick intro to back quotes. How are back quotes actually useful? You can do silly things like that. So echo hello is echoing hello. So this is replaced by the string hello, and then we are really running echo hello, which just becomes hello. Okay, so that's not really useful, but just to give you another taste of this. How do we actually make use of back quotes? So back quotes are often useful to do things like use the expression command. So I'll move the expression command up slightly, and I'll talk about the expression command here at 8 minutes and 45 seconds, very briefly. So expression lets you do basic math on the command line. So I can do like 5 plus 12 minus 5, right? Which is just 12, or minus 2, which is 15. And then I can try to go times 2. And what's this going to do? So is it going to, I'm not even asking about bracketing order. Let's try to make this less ambiguous by putting in some brackets here, braces here. So, parentheses. So this should be 30, right? This is 15 times 2 should be 30. But in fact, you get a syntax error. Why are you getting a syntax error here? Because star as a token in bash is actually being expanded to all of the files in the current directory. So in the pre-processing stage, before this command is executed, what's happening is it's looking at this and saying, okay, this is the string 5 plus 12 minus 2 in parentheses, and then this is replaced by the string all of the file names in the current directory separated by spaces, and then this is the string 2. And you can see this if I go echo back quotes. So what command am I going to run? I'm going to run the command star. Actually, that did not work nicely. Let's try. No, okay, so I won't go down that path. Okay, never mind. Anyway, it's not so easy for me to show that that's what star is doing, but fine. That's what star is doing. So you have to kind of escape this star somehow to get the desired behavior, and a backslash is how you escape special characters that have a special meaning in bash so that they're not expanded. This is one way of doing it, is to use the backslash star. And now backslash star, no, it appears I've made a silly mistake. Does expression need, you know what, I think expression actually can't do these parentheses. Yeah. And then, of course, the number is different. Let's simplify this expression slightly. Okay, so here I'll just rejig this slightly, this example. So this should be 12 times 2, which is 24 plus 5. 24 plus 5 is 29, right? But then I predict we're going to get an error because of this star here. So indeed, there is an error. And if I put a slash here, there is no error. We get 29. So I'm escaping the star. Okay, so if we have this command here, and suppose we want to echo this as part of a more complex expression, like say, echo 5 plus 12 times 2 equals, and then I want to print this expression. I can put it in back quotes, and I can actually do the math in line here. So here I have, this is just a string. And then here I'm actually evaluating the result of the expression using the back quotes. So you can roughly speaking, think of the back quotes as eval. Eval, 5 plus 12 times 2. Of course, eval is different, and this is not what we want. I'm just saying semantically that's sort of what this is doing, right? You can think of the back quotes as sort of an eval statement, and we'll see where this is useful in some other settings as well. Okay, but how about double quotes and single quotes? What's kind of the main difference between double quotes and single quotes? So let's talk about bash variables briefly. So I can set a variable here like x equals 5. I can set y equals 12 and z equals 2, and I can go expression x plus y times z, right? And this is going to give me the same computation that I had before because I have these variables, and I can assign the result to, in back quotes, that. So now if I echo result, well, now I have 29 as a result. Now, if I echo, suppose I want to echo the words $result, the actual string $result. Can I put it in quotes and get that result? No. In double quotes, $result is still expanded to the value of that variable. But if I put it in single quotes, it's not. I can actually print $results. That's the difference. Single quotes don't expand variables, and double quotes do expand variables into their actual values. And if I'm not mistaken, I think I can actually use quotes in here, and it doesn't break anything. Why does it not break anything to pass these quotes to, the expression command? Well, because these quotes are evaluated when the bash preprocessor is evaluating arguments. So what's the order of evaluation for this whole bash line, this line of bash code? Well, first, it's going to say, before I can fill in the value of this variable, I need to execute this back quote function. And so I'm going to execute this in sort of a subshell. And before I can execute this, I have this expression command. I have to evaluate all of its arguments. So it's going to look at each of the tokens separated by spaces and say, okay, evaluate this token first. The way that I evaluate this is I substitute x, and then I evaluate quote whatever is in x. Quote whatever is in x is 5. So this is quote 5 quote, and quote 5 quote just evaluates to 5. So what's passed to expression as an argument is not quote 5 quote, it's actually just 5. Then you have plus passed as the second argument to expression, and then you have just the number 12 passed as the third argument to expression. You have just the actual character star, not backslash star. Backslash star is evaluated by the bash interpreter as star, the character star. So character star is the fourth argument to expression, and then just the number 2 is the fifth argument to expression. If we wanted to pass actual like double quote, 12 double quote, then we could put double quotes that are escaped before here, and of course that'll give us an error because that's a non-integer argument. These outer double quotes are evaluated by the bash interpreter, but the bash interpreter takes backslash double quote to mean please put an actual double quote character before the 12 and then a double quote character after that. And this backslash double quote won't be interpreted properly unless you have these sort of outer quotes. You could also do single quotes to wrap the double quotes, except of course then, because it's all wrapped in single quotes, you wouldn't get the expansion of $y. You can nest quotes the opposite way as well, but of course, so that's actually interesting. I actually didn't know this right before I ran this, but if you do the double quotes and then single quotes inside, the single quotes don't count as single quotes that will prevent expansion from Bash's perspective, because the bash processor is only considering the outermost quotes, and whatever's inside is just a string, and since the outermost quotes are double quotes, substitution will happen. So that's interesting. I actually didn't know that. Maybe I'll end up finding a use for that at some point. Cool. Okay, so that's quotes. Now let's talk a little bit about redirection. So that's going to be happening at 60 and 30. Okay, so we already talked a little bit about the pipe. Okay, so pipe is redirect to another command. Okay, so this is called piping, and we can redirect, for example, to tail. Okay, and we can redirect tail. So let's say you want the line that's 10th from the bottom or 5th from the bottom in temp.txt. Here's a way of getting it. Get tail to give you the bottom 5 lines, and then get head to give you the top line of that. That's the 5th from the bottom line. So piping together commands, this is sort of the Linux way of doing things. Piping together commands to get these nice sort of chains of processing commands that end up giving you the desired output, and it's quite easy to do. There's also this, let's say we wanted this to go, let's say we wanted that to go to a file. So let me just grab this command and paste it. Say I want the output that, pappy L2 TCM equals blah, 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 to go to a file. So I can pipe this to, out.txt. Okay, so I piped that to out.txt. Now if I cat out.txt, I'll see that's what it contains. Okay, what if I do that again? Well, it's overwritten out.txt. If I do this and put double arrow, I have concatenated, so I can do this, over and over again, and I'm concatenating. So this is useful for like logging or like incrementally building up the contents of a file over a long bash script. So this is append, this is new file, this is append. How about, so this has all been standard output. What if there's an error? What if this like head-1, I like make the syntax incorrect, head1. Well, now I have this standard error message on the standard error pipe. Like all Linux output goes to either standard out or standard error. This is going not to standard out, but to standard error. Standard out is being routed to out.txt, but standard error is not. It's being routed currently to the terminal still. What if I wanted to route standard error to out.txt or even to a different file? So I can route it to out.txt by going, so this is redirect something. What am I redirecting? I want to redirect standard error. So it turns out there are these named pipes 1 and 2. 2 is standard error. So I can route standard error to error.txt, for example. Now I get no error message, right? But if I cat error.txt, the standard error has gone there. Okay. So 2 is standard error. 1 is standard out. If I put 1 here, then it's actually the same as if I didn't put 1 here, because if you don't put anything before a redirect token, a redirection token, then there's an implicit 1 for standard out. Now I can also route, for example, standard error to the same place as standard out, wherever that is. So this is standard error is redirected to the address of the standard out pipe. And so if I cat out.txt, now the standard error message has been appended there. Standard out was being appended to out.txt. So standard error is going wherever one is, even though this is like, it seems like a single arrow should be like overwriting the file. It's going to wherever standard out is, in whatever capacity standard out is going there. Okay, so this is if there's an error in this head command, sort of these redirects are being applied, just to make it less confusing, I'll put that there, to connect them so you can see exactly what's being routed. So this command's output is being routed in this way. But what about this command's output? This command's output's only being routed to head, and in particular the standard output, because there's no 1 before this pipe, is being routed there. If I put a 1 before this pipe, then that's actually an error, because piping only routes standard out, and unlike these like little arrow redirects, it doesn't support an argument there. But what happens if I create an error here? Well, notice this output to standard error cannot open 5 for reading. This is an invalid argument. This is not being piped to the same place as this standard out, because this is the standard error for this command, which is being routed to the terminal, and only the standard out from this command is being routed to head, which is then being routed. Everything from head is being, from this point on in the pipeline, is being routed to out.txt, but only the standard output from tail 5 is going onwards in the pipeline. The rest, the standard error, is just going sort of laterally out of the pipeline here. So you can actually add 2 here, going to the same place as 1. Now, if I cat out.txt, then any errors that happen here are being routed to the same place as standard out. Standard out is being routed to head, to actually the input to head. So it's being filtered here. So this isn't exactly what we want if we want the standard error to be captured. Let's say we want to capture all standard error stuff to error.txt appending. Now this is going to give the correct results. So here we have the error from tail is being routed there, and the error from head is being routed there. Is being routed to standard, to error.txt. And I'm going to test this here just to make sure. I think you can actually kind of take everything from this whole command by putting it in parentheses and say standard out goes to out.txt, standard error goes to error.txt. Yeah. So if you want to not worry about, so you can route individual commands, standard errors and standard outs, by sort of putting these redirection tokens, right after the command for each of the commands in the pipeline. Or you can take this entire pipeline in parentheses and route the output of all the commands in the pipeline at once. So that's kind of nice to know. And okay, so this is redirect to an address, to a pipe address. And here, of course, the address is the pipes. 1 is standard out, 2 is standard error. And then if you have, commands, and then route that to, out.txt, and, 2 goes to the same place as 1. This is another pattern that you can follow. A bunch of, command 1, command 2, command 3. Let's get rid of the command 3 so it all fits on one line. Command line 1, command 2, you can route the output of both of the commands to out.txt using that kind of command. Okay, and then I'm going to talk about t very briefly. So sometimes you'd like to kind of route everything to a file, but you'd also like to produce output on the console as well, and t is really nice for that. So I can pipe this to t and then a file, so out.txt. And if I want to append, this will, by default, what will this do? This will pipe all of the output of these commands to this program t, and t will print that output to out.txt, and it'll also print it to the terminal. And by default, it will delete and overwrite out.txt. If I put -a, it'll append. So here you can actually see this stuff. Let me overwrite out.txt for the moment just to see what gets actually outputted to it. So nothing in this case because there's an error message. So I actually need to route here, the standard error needs to get routed to the same place as the standard out. Am I doing that correctly? I'm piping this to t, so I need to pipe. So here, the question is, what am I piping to t? I'm only piping, by default, the pipe just takes the standard out of all this stuff. So I'm only taking the standard out of all this stuff. If I want to take the standard error, I have to route the standard error to the same place as the standard out. Now all of that will get piped to t. But t itself is by default going to still only send standard out to out.txt. So we have to send standard error to the same place. So let's send standard error to the same place as standard out. And now if I cat out.txt, it's gone to out.txt, and t has also printed it to the console. So I'm routing all of the output of this, piping all of that to t, and t by default ignores standard error, so I'm also piping all of the standard error to standard out. So as far as t is concerned, it's receiving 2 lines on the standard out pipe. This line and this line. It's duplicating those lines to the console and putting them into out.txt. When I cat out.txt, I see those 2 lines, and I see them both here. So this is like a somewhat complicated example of how all of this piping stuff works, but hopefully this will be a really comprehensive example. I'll show you the append here, so I can do this a few times. You're seeing only 2 lines show, right? But when I cat out.txt, all of those lines have been kind of appended. So really powerful utility for logging. So that's a crash course in that stuff. Now I'm going to talk about printf very quickly. So that's happening at 26 minutes into the video. So printf is kind of neat. If you have any familiarity with C or C++, you've probably seen printf before, especially in C or even in Python. Printf actually exists for bash as a bash utility. It's super useful if you want to just quickly print some columns. So, for example, I can go, let's say I have my variables, because remember, I have those variables, right? X, Y, Z. I can printf those, and I'm just going to print them as strings. You can format them however you like. I want to print them as strings that are 20 characters wide. That's it. I've configured they're going to print, columns of 20 characters wide. They're going to be printed as strings. And so I'm going to print $x, $y, $z. And that's it. There's printf nicely formatting these things. Now, did I need to put these $x, y, and z in quotes? No, not really. But the trick is, what if these variables can sometimes be empty? If these variables can sometimes be empty, for example, now if I set x to just nothing, and I printf, now it's as if there's no x column at all, and y gets printed in the x column. Because once the bash interpreter starts to process this line, it first evaluates $x, which evaluates to nothing. And so this just looks like space, space. And bash is space invariant. It doesn't matter how many spaces I have here. All the spaces get collapsed into one space. So it's as if this token doesn't exist at all. So it's as if I just wrote this. And that, if you have headers for your fields and you don't want your fields to move around if you have empty fields, then that's probably not desirable. So what you want is to put them in quotes, not single quotes, because then they won't be expanded. And then here you'll just get an empty field as you desired. Okay, so that's kind of a crash course on printf. Of course, you can look at the man page for printf to see, all of the different formatting, strings, etc. But this is really nice for printing, sort of columnar output from your experiments and things like that. Okay, so let's talk a little bit about if statements next. So that's going to be happening at 28 minutes and 20 seconds. And we'll just do a little bit of a crash course in if statements. So suppose we want to branch based off of whether, x is empty or not. So we can go if $x is empty, then echo it's empty, else echo it's x. And we'll put that in quotes, and I just learned that I can do single quotes around this because of the outer double quotes in bash, and it'll still substitute for the value of x, and then you finish an if statement. So if statements are if something in square brackets, semicolon, then whatever's in here. You can have a bunch of semicolons in here. Doesn't actually matter whether you've included white space or new lines or anything. And then else, and then you can have a bunch of lines in here separated by semicolons, and then phi. So if is terminated by phi. Okay, so it says it's empty. Now if I set x equal to 5 and rerun that command, it'll say it's 5. So here's branching on just a basic test for whether something's empty. There's some other things you can know about if it has, I mean, you should, check out the man page for test, which is this square bracket stuff. That's where you learn what you can do in these square brackets, all the different conditions you can test. So, some useful examples are -d. Is this a directory that exists on the file system? So it is bin. In fact, I don't even need the double quotes if I don't have any special characters or anything. If bin is a folder, then echo it exists. And I won't even have an else case here. I'll just have v. So it prints it exists. And indeed, if I ls, you can see the bin folder. How about if foo exists? Foo does not exist, so I don't get this print statement here. By the way, if you want to know how to check return statements of things, which may be useful at various times, $? is the variable for return statements. So if I do like a ls foo, that's a failed ls execution because that folder doesn't exist. So if I echo the return code, you can see that it's a non-zero return value. If I ls something that does exist, bin, and then echo $? It's a 0 return value. That's a successful command. So you can test for command success by going if $? And then, let's try equals 0, then echo success. I don't even need the quote if it's a single word. Success, phi. Okay, so that's success. Now, I wouldn't normally recommend using this equal sign. If this is numeric data, you're actually supposed to use -equals. And you can also use greater than, less than. There's greater than, less than, greater equal, less equal, not equal, equal. Anyway, you can use equal. If it's like a string comparison, then you can do not equal. So this is a string comparison. Whoops. And these are numeric comparisons. So this is testing for success. And by the way, the control C here counts as a fail, I think. Yeah. So if I control C and then test was it a success, I get no, it's not. But now is that a success? Yes. So there you go. That's testing for success. And a little bit about those square brackets and about ifs. And so these are string equality and these are numeric equality. Now there's another format for if statements which sort of piggybacks on C++ syntax. So you can go if, for example, and I'm just gonna, I tend to use the square brackets myself, but this is actually quite nice. I don't mess around with it enough, so I'll bumble around here a bit and we'll figure it out together. So let's see, if x equals 5, then echo success, phi. Okay, so success, x was 5. Notice I don't need $x, but I can put $x here. If I put $x, then what's happening is the bash interpreter is replacing $x with 5, and then it's executing if 5 equals 5. And anything in double parentheses goes to a C++-like interpreter before it gets handed off to bash, and this gets substituted with like a success or fail code. So I can do $x, but within the double parentheses, it understands that variables you're referring to here are bash variables that exist, so you don't actually need the $signs. I can do if x is, greater than or equal to 3, right? So it is greater than or equal to 3, right? It's 5. Is it less than 3? No, fail. So I can do things like that. I can do if x times 2 is less than, divided by 2 is less than 3. Okay, that's success, because 5 divided by 2 is less than 3. How about if do I have to escape the star in there? No, I don't. So again, because it's in the double parentheses, bash knows that it's not going to do its pre-processing step where it replaces star with a bunch of file names. So you can do nice math inside this. And if I'm not mistaken, I think you can go x over 2 times 1. Oops, I missed a... do that. Okay, so that's got an error message, so I can't do that. But I think I can do $sign that. Yeah, so you can actually get evaluation of these things, in order to do assignments to variables for some sort of quick math, by just prepending a $sign in here. So in the if case, you don't need the $sign, but if you're like trying to just execute something on the fly, you can put a $sign to evaluate it that way. Yeah, so a $sign, double parentheses will let you evaluate a bunch of math stuff. So that's kind of, and then $sign, double parentheses there. It's not really part of if, it's actually just kind of separate, because you can see I can do it here in the echo, but I'll put it there anyway. Okay, so we're going to talk about for loops now, so we're at 34 minutes and 30 seconds. Let's talk about some for loops. So for x in ABC, do, so the for syntax is for something, semicolon do, and then a bunch of lines for what you're going to do. In this case, I'll just go echo x, and then done. For, do, done. Okay, so we can do something for each of these, right? We can do, if x is a, then echo found it phi. So all it's going to do is it's going to iterate over all of these, check for each of them, string equality comparison to see if it's a, found it on the first one, right? And then, for example, we can do, let's see, we want to figure out which index it is. So we'll go I equals 0, semicolon, and then we'll go at the end, so we'll go found it at index I, and then before we go to the next iteration of the for loop, at the done, we'll go I equals $i plus 1. So found it at index 0. Okay, that sounds good. What if we're looking for b? Found it at index 0. Well, that doesn't seem right. So let's see here. I messed something up. I don't normally use this $sign syntax, so I'm kind of curious. Echo I. I is 1. So what did I do? So let's just run through this. So we have for x equals ABC, do I equals 0. Oh, that's happening inside the for loop. So initializing I to 0 in the for loop is pretty clearly a problem. So let's set it at the beginning. There we go, found it at index 1. And then B, C found at index 2. So this is, obviously a super contrived example, but you can see how you would do some basic stuff with the bash for loop here. How about different formats for bash for loops? They have this range notation, which is kind of interesting. We could do this with numeric identifiers too, right? So let's just change this slightly. Let's get rid of this if, and then let's just echo I equals I, x equals x. Sorry, I've got the phi still in there. Okay. Yeah, so in iteration 0, we had x equals 1. Iteration 1, we have x equals 2. In iteration 2, we have x equals 3, and so on. So you can iterate this way over, numeric things as well. And we also have this, syntax where you have this sort of range expansion. And there is, there are more syntax options for this, like a step and stepping down and so on. Let's just print that to show that that works. And then you have, again, this double parenthesis sort of C++ style thing. So you can x less than 10, plus x, do echo x, done. There you go. And you can do, it doesn't have to be this simple, right? It's not, this is really just like a kind of a C++ style evaluation. So I'll do my silly example here. X equals x over 2. There you go, 50, 25, 12, and then 6 is less than 10, so we don't print. So you can do pretty complicated things in there. So that's bash for loops. Let's talk about some sort of very powerful file manipulation, text manipulation, text processing, data processing commands here. So I want to mention word count fairly easy in this, just because it's super easy. Did I say easy in this? I meant to say early in this. So let's take a look at grep. Grep is like, grep and cut and tr are some of the most useful utilities that I know of. I use them every single day in doing any experimental research. So let's see, we're going to talk about grep at 3845. And by the way, this is all a single long take in case you were wondering. So let's cat temp.txt to grep. Okay, first of all, let's cat temp.txt and sort of say, well, what kind of stuff as an experimentalist might we want to extract from this file? So first of all, this is kind of how I tend to make my experiment output files look. It's a huge amount of just like human readable stuff. And I did cut and paste and move some stuff around, which is a little silly when we were text editing this. But you can sort of see a lot of the data that's here. Like any sort of like arguments that are, like parameters of the execution are there. Oh, I shouldn't select things because that brings me back to the bottom of the document. So we have sort of a lot of arguments, parameters of the experiment, and I cut and pasted a bunch of those parameters down here as well for no reason, just to demonstrate the micro editor. So, all these parameters, we try to print them so that we have them all available, and I tend to try to print things in a standard format, like, alphanumeric characters with underscores equals something, usually numeric, or else I don't care about it, or I don't want to export it in like a CSV format. And then, I tend to output tons and tons and tons of data that's human readable, and I really don't emphasize producing like CSV formatted, stuff that's not human readable but machine readable stuff in these types of like files. And I'll produce thousands of these files as I run experiments, and they're all named, and there's sort of links between the spreadsheets and the names of the files, so that I can always easily go and drill back down to this full text file that I keep for each experiment. And after I've produced these files, then I filter these files and turn them into the CSV data that I want. And it's really nice to have sort of separation between the data that's being output by your program and the data that's actually being fed into a spreadsheet or some data processing program, because that means you don't have to rerun all of your data, all of your experiments, in order to extract a little bit more information in the CSV, or shuffle the columns around in the CSV. It just decouples the running of experiments from the parsing of the results into data that you want to then process using data processing tools. So what this means, of course, is I have to have a pretty strong command on these sort of text processing tools to extract the information that I'm interested in and turn it into a CSV format. And I find this at this point super easy. I can do this in 20 seconds or something, parse this, thousands of files like this. I'd say well under a minute I can parse thousands of files like this into a CSV format, extracting exactly the info I want. So how do I do that? So the first thing I do is I sort of prototype rapidly, extracting the kinds of data I want using grep. So what is grep? Grep is a tool that extracts lines from a program, and you can actually use regular expressions in grep, which I will use here. So I want to extract anything that uses lowercase letters or capital letters and underscores, and has at least one character of these, and also as many as I can grab, until I hit an equals sign. And then I want to have only numeric data and maybe a period. And I have to escape the period because in regular expressions, a period just means any character. So I actually want to escape the period. And I want to ignore entries where it's just, something equals a blank. No, not even any number. So I want a plus, at least one character. And okay, so this is a good first regular expression. Let's see what that pulls out of the temp.txt. And it highlights it in red so I can kind of see what it matched, what grep matched. And you'll notice it's pulling, so these things look really great for placing into a CSV. But these things don't look so good for placing into a CSV. So I kind of like to get rid of these lines. And they've got these spaces that are not being matched by the regular expression, but they're being included, because the regular expression is like, if it matches anywhere in the line, include that line. And so we can control that by using this caret means the line should start with this. And then the dollar sign means the line should end with this. This is saying the line, the entire line, should exactly match some alphabetical characters, lowercase and uppercase, and possibly underscores, a non-zero number of these, followed by an equal sign, followed by a non-zero number of 0 to 9 digits, and possibly periods. Okay, so that actually cuts out all of those, and now I have a pretty good candidate for stuff that I'd like to turn into a CSV. Okay, so how do I turn this stuff into a CSV? We're going to turn to cut. So cut, we're going to introduce at 43 minutes and 45 seconds. I guess I'll talk about word count after I get through cut and tr. Okay, so cut is a tool that basically tokenizes the input. You can think of it as like the C str string tokenize function, or the Python split function, or the Java string tokenizer or split functions. It tokenizes your input by some delimiter character. It does it line by line, and then you can select only some of the columns according to that tokenizer delimiter. So I'm going to pipe this to cut. I'm going to set the delimiter to the equals sign, and then I'm going to set the field that I want to extract to just 1. This is going to get the names of all these fields. That's it. And by the way, I can go 1, 2, and I can pull both of the fields, which is kind of interesting. And it's going to put the delimiter back, which really just gives us our input back. And if I select 2, that's going to give us just the numbers. So I can get the header for my file sort of this way. I've got all the names, right? But I still have to turn this into like a nice looking CSV header. So what I'm going to do, I kind of want to take this input and replace all of the new line characters by commas. So how can I do that? I use tr. This is called translate. It replaces characters by other characters. It can also delete characters and squeeze consecutive repetitions of the same character into a single character. So I'm going to use tr to replace \n, which is new line, with comma. And that's it. Now I've actually just in a single command extracted from temp.txt a header for my CSV file. However, it turned even the last new line character into a comma, so I don't have a new line at the end. So I'm just going to semicolon echo to add a new line at the end. There, that looks kind of nice now. So I can pipe this to a header file, header.txt, and oops, that didn't quite work, right? Now everything looks all kind of screwed up. What happened there? So, I mean, I know, but I'm trying to think of the right way to say this. So the echo command is having its output piped to header.txt. So if we cat header, we just see there's just a single new line in there. So what we really want to do is put parentheses around this stuff. And now we're going to pipe everything that was output to header.txt. Okay. And if we want to just sort of preview what's being output to header.txt, we can oops, sorry, not arrow, but pipe to t, and then we see. And of course, if we cat header.txt, we see the same thing that t showed us. Okay, so we have a header. Now, how do we get our data? Well, we're going to cat temp to the same regular expression, but pull out the other, so -a to append data.txt. In fact, we can just append it to the header file because we're appending. So it's not really a header file. We sort of started our CSV. So field 2 is going to be the actual numbers to the right of the equal sign. And if we cat header.txt, we have the header and we have the data. And if I bring this into micro just so it's sort of easier to see, you can see that that's really 2 lines. So this is how to process really nice CSV data. Now, of course, it's not really header.txt, it's like data.csv, right? So that's sort of what we've started off here. And now, okay, we processed a single file, but in reality, you don't want to process a single file, right? You want to process lots of files. I also briefly want to show you some other features of grep and tr. I'll just tell you for grep very briefly that grep can accept kind of all of the basic regular expressions that you might expect. You can also invert the regular expression. So if you're grepping and you're going -e and you have some regular expression, you can return all the lines that don't match this regular expression by pressing V to invert the regular expression. So that's quite nice to know about. So nice to know about -e is to enable extended regular expressions, and -v is to invert. For tr, you also have, for example, this. Oh, let's use ps as an example. So ps here, you have sort of like multiple spaces that you'd kind of like to get rid of sometimes. Sometimes it's nice to mash these spaces together, and you could sort of split this up by spaces as long as you mash, let's see, these things together. So you might want to pipe this to tr-squeeze spaces. So all the spaces have been squeezed together now. And if you also, so now you could split this up using cut into columns, with the single exception that you have for these small numbers, you have this stupid leading space. So you could write another little utility that would just trim a leading space if one existed. I'm not aware of one in Linux that just does that in particular. There's no like trim command that I'm aware of, but if you write a little tool that you sort of accept a pipe and cut off this space, then smashing all the spaces together means this thing that's human readable all of a sudden becomes machine parsable, because you can split columns by spaces and deal with the fact that there's a variable number of spaces because you've squeezed things together with -s. You can also use tr to delete characters, so you wouldn't really want to do this, but you could delete every space in the entire thing. And I suppose you could do this and then sort of parse according to, like, you could split the string according to, like, the letter P to get the PID of something, and then you could split it according to, like, colon, and then, you know, chop off the first two characters to get the executable or something like that. So you sort of learn to think about this stuff if you're really interested in text processing, you know, chaining up all the different tools that you have. So I can, you know, I can go cut dash dp dash f1. There, now I have all the PIDs, right? So that's kind of, you know, useful to know. So you should know about dash s, dash d. So that's, you know, replace is sort of the default. Then you have dash D for delete and dash S for squeeze. And I'll also mention word count. So if I pipe to word count dash L, that'll tell me how many lines there are here. There are 30 lines. Just a nice tool to be able to quickly, you know, if you want to get like num lines equals this, echo num lines, you know, then you can go, that's interesting that the word count was different. Oh, that's because the word count, so I printed the word count and it was 30, and then I did this and the word count was 31. That's because this back quote spawns another shell, and so when we execute the PS command, there's an additional shell for a 31st process ID, which is kind of cute. Yeah, and then you can echo num lines, and you can use num lines in your scripts. If num lines is less than 30, do this. If it's greater than whatever, you know, so... you know, word count is a really nice tool for that. Word count has a few options. You can go, you know, ps dash a pipe to word count. It gives you the number of lines, the number of words, and the number of characters. So you can go dash w for words, dash c for characters, dash l for lines. Just really nice for sometimes counting how many files there are in a directory, you know, and so on and so forth. So you can know about dash c, dash l, dash w. Let's do them in that order. Okay, so that was word count. Now we're going to talk a little bit. Well, let's give an example of trying to actually use some of these tools that we've put together to run a non-trivial experiment here. So I'm going to go history grep. So history is a nice tool to know about. It tells you all the commands you've typed, all of them. And then if you use 2,000 something of them, if I pipe them in a grep, I can actually search for commands that look like, you know, something I'm interested in. So I'm interested in finding ubench commands, and I only want the last like 3 that I ran. Okay, so really nice to use grep in conjunction with history to figure out things untitled, to figure out things you've run. So here's a simple command. This is actually how I generated the temp.txt file, as you can see here. You know, here it is. If I run it, it produces this nice output. And say we want to run this for a bunch of different thread counts. Okay, the right way to do this is with a for loop. So let's let n be the number of threads. And then on this system, let's say I want to run 1, 2, 4, 8, 12, 24, 48. Okay, semicolon do, semicolon done at the end. And we're going to replace the number of threads that are running in this concurrent workload with n. Okay. So if we run this, well, I mean, we get this massive amount of output that's totally unintelligible and it's not being saved anywhere, right? So let's cancel that. Let's actually save this output. So we'll save this output to temp.txt. Well, each of these iterations of this loop, we're going to be overwriting temp.txt. So I'd better parse the temp.txt file each time, or maybe I should save these as different files. So I'm going to call this step $n.txt. So I'm actually using n in the file name, and I'd also kind of like to know what my progress is, so I'm going to echo, you know, produced step n.txt at the end of each iteration. So now when I run this, we'll see that I've produced step 1, and then I've produced step 2. Oh, I'm getting segfaults. That's interesting. In fact, this data structure has some problems, so to avoid having weird outputs, maybe I'm going to run a different data structure, and we'll see how that works. That shouldn't Oh, well, okay. Maybe I've got some weird settings going on. I'm going to pause the video and investigate that briefly. Okay, so that didn't take me too long. I thought you might be curious to know how I actually debugged that. So what I did was I started from our command that we had here, and I said if there are seg faults happening at one thread, I think I just want to cut down my end to one thread, and then I want to see the actual just raw output. So just modifying our command very slightly and running, and then there happened to be no seg fault this time. Let's try running again. It was sort of sporadic. Interesting. Now I'm actually not seeing it. Huh. Well, of course this happens when you're sort of ad-libbing things. Anyway, I'll tell you what happened. So I modified the command as we showed here, and the seg fault did happen repeatedly, and then I wanted to run this thing through GDB to basically trap the seg fault. So I typed GDB here, and then I need to pass these arguments to GDB because it wants them in a particular format. So I go -x, which is a command for GDB to execute, and the command is set args, and then you just supply all the bash arguments. And that's it. I've modified the command appropriately to run in GDB, so I press enter and I go run, and I wonder if it'll seg fault this time or if it'll terminate normally. Yeah, so it actually terminated normally. In my case, it seg faulted. I found what the problem was. It was like an erroneous delete. I'm not sure why it's not happening now, but I won't spend too much time thinking about it. I'll spend some more time on it after I finish the video. At any rate, that's sort of how you plug in GDB easily in this kind of framework. Like once you've got for loops and a big command that you're working on, it's not too hard to tweak that command to do some debugging. I would, cut down the number of threads to the one that's faulting, delete the sort of output and processing stuff at the end of your command. So instead of saving to a file, I'm just outputting to the console and run it through GDB. At any rate, let's proceed as if nothing's wrong and just see what this looks like generating data. So we're going to run this script and generate data. Hopefully we don't get any seg faults here. And we've produced, so step 1, step 2, step 4, step 8 is about to finish, and I'll jump ahead in the video here. Okay, so we've jumped ahead in the video, and now we want to see what happens, how we're going to sort of process all of these files. So I'm just going to run history and scroll up to where we were actually processing files. See, we did this to output all of the data, so I'll copy that command, and we're going to run this basically for all of the files. So what we want to do is first I'll just set the file to one of these to test. So f is step 1, and then I just like having a variable for the file name because it's sort of easier to think about. I'm going to just swap out the specific file I set for a loop variable, and we'll do the same thing for all of the the file names. So we're going to output the data for this file to data.csv. Let's just remove data.csv as a first step, and we'll cat data.csv, and it looks fine. Okay, so we kind of need, what do we want to do? We want to create a header, right? So with the first file, let's create a header. Okay, so I'll copy that whole command. Here we have cat f to this, and we'll pull out the first column before the equal sign, which is the names, and we're not going to append. We're going to start a new data.csv, so I don't need this remove data.csv file. Okay, so we're going to create data.csv with a header, and then in this next line, we're going to append the first file's data. So if we cat data.csv, it looks like that. And of course, we could see that from T, right? Okay, so that's our header. And then after the header, we have this sort of one-off here where we'd actually, this one-off printing of one file's data where we'd actually like to do this for each file. So what I'm going to do is for f in, and now I'm going to try to just use bash. The fact that bash will, in its interpreter step, replace this star to match all files. We're going to abuse that to iterate over all the files in the current directory that are called step whatever.txt, and we're going to execute this for each of them, appending them to data.csv. So let's see that work. And it does. And now we actually have all of our CSV data. So if I weren't narrating and being very careful about writing this command, I could write this super easily. And once, of course, I've written this, I can just kind of take this and, create a parse shell script where, I can break up these lines and whatever. But once I've sort of prototyped it on the command line, now I have a parse script that produces the desired data.csv, and of course I can reuse my parse script over and over again. And this was very, very easy to come up with. This is the kind of thing, this is like a throwaway script that takes me a few seconds. And of course we don't have to pull out, everything that's equal to, every line that matches some text equals some number. We could filter this more, we could write different regular expressions here. We could write a script to produce a regular expression that we're then going to feed to this. That's an approach that I actually took in this project, where I have a parse script where I actually highlight all the fields that I'm interested in, just sort of build a big string out of all those fields, and then I grep for, I actually iterate over each of those fields and grep each field individually. I just wanted to process them one by one for a few reasons that I won't get into. But yeah, you can build a big string, a big regex string even, that will capture everything you're interested in. Okay, so that was an example. I think that was, example of processing data. I think that was around 50 minutes if I'm not mistaken. I can tweak that after the video to fill that in. I'll put some question marks to let me know. So I'm also going to talk very briefly about while read and awk. I'll just give a very simple example of that. So let's think about, let me get rid of this really long text file here so it doesn't sort of mess with how I want my screen to look. Okay, so let's think about sort of parsing this input. Suppose for whatever reason, I had a very straightforward desire for how to take this input. I mean, this is just a proxy for what you would want to do in a real program or in a real, experimental scenario. Obviously, there's no reason you'd want to do this, or no real reason I can think of where you'd want to do this, but we're just going to use this as an example. What if you wanted to take this input and transform it so that you have this column followed by this column, and we sort by the contents of this column from largest file to smallest file. So how could we actually accomplish that feat? So one thing we could do is we can pipe the output of L to tr, which is going to squeeze the spaces, because we have all these spaces here, which sort of make it, the variable number of spaces makes it sort of challenging to slice this up into fields by spaces. And then we can pipe this to cut, where we're going to grab with a space delimiter fields 2 and 3, 4, 5, 6, 7. So 2, 7. Okay, now we have those. And just for simplicity's sake, let's get rid of the ones that have a dash in the first column. So let's go grep dash E for extended expressions, V for reverse, and we're going to look for lines that start with a dash, and dash is a special character in regex, so I'm going to escape it with a backslash. So now we've gotten rid of all the lines in the first column, and we can pipe this to sort dash n for a numeric sort, but of course that's not quite right because we have these k's in here. And so we sort of, we'll think about that later, we sort of want to multiply out those k's, and let's say we also want, of course, to swap these two columns. So one way of swapping these two columns is to pipe all of this to while read. So while is just a while loop. The syntax is while, semicolon, do some stuff, done. But while read in the condition, so there's a condition in there, which you can have like square braces, then semicolon, do, or you can just have a read statement. And a read statement is saying, while there is a line of input to read, I'm going to read some tokens from that, space-separated tokens. So what I'm going to read here is size and name. Do echo, just as a test, let's echo size equals size, name equals name. Done. Okay, so now we've sort of taken these two columns, parsed them into these variables. Within the while loop, we have access to these two variables, and we printed these variables. So if I want to swap these two columns, pretty easy, right? I can just do $name, $size. There, I've swapped the two columns. But now I want to first sort properly, descending by size. And so before we swap these things, let's output size and name. Let's keep the size first because sort by default sorts on the first column, and let's do a little bit of math to modify these sizes. So let's have an if statement that says if the last character of size is k. Well, that's kind of hard to do. It's a little bit hard to write that expression, but we have tr that deletes characters. So what we can do is we can say if size is equal to, string equal to, let's do back quotes, and let's actually use tr. Let's echo size to tr and delete the letter k. And if the letter k, when we delete it, if we delete the letter k from size and we still get the same thing as size, that means it didn't contain k. So that means we can just echo the size as is. Sorry, I need a then. Otherwise, we actually have to multiply by 1,000 because we've removed the k. So I'm actually going to simplify this a little bit. We can create a new variable here. So I'll call it no k equals echo size pipe to tr-d k. So we're going to delete the letter k. That's no k. If size is equal to no k, then we're going to echo size. Else, we're actually going to echo expression no k times 1,000. Only expression doesn't handle decimals. So because expression doesn't handle decimals, we're actually going to talk a little bit about BC here. So the BC function we use by echoing the expression that we want to compute, which is no k times 1,000. We echo that to BC. And then we're also going to echo name. And let's just see that work. We have phi to end our if statement. And of course I've made a mistake because I wrote something big and complicated here. So let's see if we can find the mistake relatively quickly. So I have various ways of doing this, usually deleting large parts of the function, but I'd rather just sort of eyeball this before I delete anything. So it's all being piped to while read size name. We have a do for the while loop. And then we have this expression, which looks fine to me. Then we have an if size equals this. That's fine. This could be a numeric comparison, but I don't mind this being just a text comparison. Then echo this stuff. Else, that semicolon I think is a mistake after the else. It doesn't like empty statements in an else. Okay, now I am printing the adjusted size, the proper size, but we have these trailing dot zeros, which is sort of stupid. BC is because in the input these had dots. BC is going to say these are floats, and then it just always prints a trailing zero. If the result is 0, it always includes a decimal place. So we can actually implicitly convert this to an integer by doing integer division by 1. Okay, so now it looks pretty good. The sizes look good, but we're printing these on separate lines. So that's kind of not desirable. We want to print these on the same lines, and it's because we have these two echoes. Yes, I suppose it's because the BC is actually printing a new line. And so one thing we can do is we can just take the result of this BC and make it a string. String equals the result of this BC. And then when we do the echo, we can echo string and name. Okay, now we want to sort. We want to take the output of all of this. We take the output of the done. This is the output of the entire while loop all the way up to the done. So this is in between these two pipes. This is doing all this processing. We want to pipe all of that to sort, and we want to pipe it to sort numeric. Now we're going to numeric sort, and we want it to be reversed. Numeric reversed from largest to smallest. And now we want to swap these two columns. So we could swap these two columns by doing a while read size name, and then do, and then print name and then size, echo name and then size. But I want to show you another way using awk. So awk is another way of processing fields and columns in individual lines. It sort of just implicitly tokenizes these things, and this first column will be called $1, and the second column will be called $2. So here's how we're going to do this in awk. We're going to say $temp equals $1, $1 equals $2, $2 equals temp print. So that's going to swap our two columns, and there you go. And, you know, just for fun, if we wanted to pretty print these things, we could by using printf or whatever else. But this is a rather complicated and long-winded example of how you chain up all of these different things to accomplish something actually quite complex on the command line. So I wanted to sort of, you know, for this last example, I really wanted to kind of explain how this stuff works, you know, in the context of some example, even if it's contrived. Just I want to show, because I can tell you about all these tools individually, but it's quite hard sometimes to see without a lot of experience how you can combine all these tools to do really non-trivial stuff. So I hope this is helpful, and thanks for watching.